Okay, let me start by telling you about the sort of one of the main objects in this theme about the metal-rich white dwarfs, what they are, why they're interesting, and so on. So metal-rich white dwarfs, as the name speaks for itself, are the white dwarfs which have some metals in them. These are the white dwarfs with the spectra showing signs of absorption lines of different metals: magnesium, silicon, calcium, and so on. And the first example of this class, the so-called 1, MAN, and 2 star, was discovered actually in 1917. It was a third white dwarf to be discovered and the first isolated white dwarf. All the previous ones were in binaries. And actually, it was not recognized that this star is a white dwarf for quite a long time. Van Manen actually thought this is this is an A star with a very small luminosity, which actually it's pretty close to truth. But now we know that these metal-rich white dwarfs are quite common, and in reality, they can comprise up to 50% of the whole white dwarf population. Current numbers are, if we are talking about some particular class of white dwarfs with a hydrogen-rich atmospheres, are something on the order of 30%, but this number, as I said, can be as high as 50%. And we usually discriminate white dwarfs according to the properties of their atmospheres, because white dwarfs are typically objects which are sort of convectively stable, but on their surfaces they have a very thin layer which is convectively unstable. And depending on the composition of this layer, whether it's composed of hydrogen or helium, we call these stars DA, which is which is a hydrogen-rich white dwarf, with the atmosphere composed primarily of hydrogen. Or DBs, this would be the helium-rich white dwarfs, and the name stands basically for dwarf A star, dwarf B star, because the spectra show lines of either hydrogen or helium correspondingly. And then Z stands for metal richness. So whenever you see this notation and you see Z in the name of the object, that means that this white dwarf is really enriched in metals. So just to characterize better this particular object, which is actually the most metal-rich white dwarf known to us so far. Yeah. Okay. Let me quickly go through this table, which sort of shows its properties a little bit better. So first of all, this white dwarf is a pretty old object. It has a cooling age of about 600 million years, which means that after going off the main sequence, it has been passively cooling for about 600 million years. It's a remnant of pretty massive star with a mass of 4.4 solar masses, so that's why the mass of this white dwarf is pretty high. It's 0.9 solar masses. Its current effective temperature is around 14,000 Kelvin. And what's important for us are the different abundances of various elements in the atmosphere of this white dwarf. This one is a helium white dwarf, so all the elements in this table are referred with regard to helium. And if you look at this table, you see that there are some effectively trace amounts of oxygen, magnesium, silicon, calcium, and so on. We actually have a pretty good idea of these elements. They are measured very, very well because the atmospheres of these white dwarfs are quite transparent. And with high-resolution spectroscopy, you can measure abundances of these metals quite well. But what should really strike you is this particular number, the first entry. This is hydrogen over helium. You can see that the abundance of hydrogen in this object is way lower than, let's say, the abundance of oxygen, magnesium, silicon, and so on. This is very, very unusual for the objects in the universe where hydrogen is like the dominant element. Another interesting point to note is that this object has undetectable carbon, which is also an element which is a metal, basically, which is quite spread in the universe. Okay, so what's surprising? I mean, what's surprising about the presence of these metals in the photosphere of this particular white dwarf? I mean, we know, for example, that if you look at the sun, we see all these absorption lines of metals. So finding a star that has metal lines is probably not so surprising. The problem is that these heavy elements are not supposed to be in the atmospheres of these white dwarfs. And that's caused by the fact that white dwarfs are very compact objects, and as a result, they have enormous gravitational acceleration in the outer layers. As a result of it, any heavy stuff, any kind of, I don't know, dust particles that you sprinkle into this atmosphere will very rapidly settle down and should vanish from our line of sight. they should vanish below the photosphere. And in this case, metals play a role of this sort of heavy stuff. So that's why we should not really see any of these metals. Now, the outcome of this gravitational settling really depends on what is the settling time. And the settling times have been calculated back in the 80s when people were starting to get interested in this area. Charles Alcock, for example, contributed a great deal to figuring out these issues, such as what would be the time of the rain down of metals from the bottom of this outer convective zone. Of course, in this outer convective zone, all the elements are supposed to be well mixed. So, and these plots are showing you the situation for the helium, for the hydrogen-rich models, and for the this is hydrogen-rich, this is helium-rich. These are settling times of a particular element of calcium, and they are shown for different white dwarf masses. These are these numbers, and for different effective temperatures. Well, the oscillations are caused by the ionization transitions in these particular elements, in hydrogen or helium. And this enormous dependence on temperature is caused by the fact that opacity is a very strong function of temperature in these regimes. And then the opacity, it's the opacity that determines what would be the depths of this convection zone in which the elements are well mixed, and the conditions at the bottom of this convection zone where the rain down is happening. Of course, if the higher density at the bottom of the convection zone, the slower this gravitational settling will be happening. And because of this, extreme sensitivity to temperature, we have tremendous differences in the settling times, for example, for helium or hydrogen, and for different masses of the white dwarfs. But the important point, yes?
For higher temperatures, you see that the settling down is much quicker, right?
Yeah, it's like days.
Could it be that when the star starts hot, then everything settles down, and then is the integral of the cooling the time it spent in the time it spent in each temperature is longer. Or what dominates settling down is long times?
So early on, when it's very hot, the settling time in principle is like 0. I mean, it just drops immediately. You can see it's days for the hydrogen-rich white dwarfs. For the helium-rich ones, it's years, but it's still extremely short. So it should all settle down. At high temperatures, you have a different mechanism. You also have radiative levitation that should keep these metals up in the photosphere. But that radiative levitation becomes unimportant at temperatures of about 20 to 30,000 Kelvin. So it should vanish, and gravitational settling then will cause this rain down of the elements. So the key point to take away from here is that these settling times for white dwarf is a mass of about 0.5 solar masses or so are so short that they are much shorter than the cooling age of the white dwarf. So in principle, any metals with which the white dwarf has started past the main sequence, they should have vanished. They should have all settled down below the photosphere, and we should not see anything in the photosphere. We should see either pure hydrogen or either pure helium, depending on what comprises the white dwarf atmosphere. And so now we should be wondering why there are any metals in the photospheres of these white dwarfs. And the obvious answer to this question was first proposed by Alcock and Illarionov in 1980. They proposed that, well, quite naturally, that these metals are accreted by the white dwarf simply from the interstellar medium. As the white dwarf moves through the interstellar medium with some velocity v, it should accrete matter at the so-called Bondi rate, which is given by this very simple formula. And if you plug in the numbers and do a simple numerical estimate, you get the mass accretion rate of order 10 to the 6 grams per second. Grams per second actually is kind of the typical unit in this field, so just get used to it. Don't try to convert it to masses per year, solar masses per year. And in principle, and you can actually measure these mass accretion rates in the white dwarfs. How you do this is you basically have a theoretical calculation of the depth of the convection zone. You measure the abundance, spectroscopically measure the relative abundances of different elements. That gives you the total mass of a particular element in the outer convection zone. And then you divide this mass by the settling time, which sort of gives you a steady state m dot, which you can measure and compare with this estimate. But one other important point regarding the possibility of interstellar accretion is that it should be bringing in material with an interstellar composition. That is, it should be bringing in a lot of hydrogen because hydrogen is a main constituent of the ISM. And that's not true. That's the biggest problem with the hypothesis of interstellar accretion. That problem is that we do observe helium-rich white dwarfs. We do observe white dwarfs which have photospheres primarily comprised of helium and not of hydrogen. And if you start accreting ISM, if you start accreting a lot of hydrogen, what will happen is that hydrogen will actually coat the surface of the white dwarf because it's lighter than helium. And so it will float on the surface, and the helium will be hidden. So all the white dwarfs, because of the interstellar accretion, should actually be dA white dwarfs. They should all have hydrogen atmospheres. And that's not happening. We see that a lot of white dwarfs are actually helium white dwarfs. And that's basically a killer, complete killer for this ISM accretion theory. Yes, Tim?
So presumably this does happen even if it can't explain the metals.
Yes.
Is it then surprising that you see things like that metal-rich white dwarf that's almost hydrogen-free at 600 million years?
It's a little bit surprising, yes. So there are trends when you look at the abundance of, I mean, even in this helium-rich white dwarf I showed, there was some trace amount of hydrogen. So you can try to see if there is any correlation between the amount of hydrogen and the age of the white dwarf, hoping that this amount of hydrogen will actually be increasing. And you do see this trend. But the m dot that you get from it is actually lower than what you get from the simple Bondi formula. That actually is not surprising because we know the same problem exists for the isolated neutron stars. If isolated neutron stars were accreting at the rate given by m dot Bondi, we would see a huge number of basically bright X-ray sources in the sky because there are like something like 100 million of isolated neutron stars in the galaxy. We don't see this. So there is apparently some problem with the accretion from the ISM given by just the Bondi formula, but it's not endemic to the white dwarfs only. Anyway, another problem is that this number which I showed before, this 10 to the 6 gram per second, is actually very low. It's sort of at the low end of the mass accretion rates which are measured in the white dwarfs. And we typically very often find objects with mass accretion rates which are 4 or 5 orders of magnitude higher. So accretion from the ISM cannot explain the abundances of metal simply from that regard as well. But the compositional argument is, of course, much stronger. So for some time, because this problem could not be resolved in a simple way, for a long time, people just stopped thinking about this problem. And the next page in this field was open only in 1987, when people first discovered debris disks around white dwarfs. So in 1987, Zuckerman and Becklin used IRTF on Hawaii Infrared Telescope to take a spectrum of a particular white dwarf, G2938. They discovered that on top of the sort of black body spectrum of the white dwarf, there is some infrared access, which at the time there was a debate what it is due to, whether it's due to the presence of the dust around the white dwarf, which intercepts the radiation of the white dwarf and re-emits it in the infrared, or whether it could be due to the presence of the brown dwarf orbiting this particular white dwarf, or just kind of foreground or background object. There was some interesting story regarding the actually the oscillations in the infrared, which were detected at frequency of, I think, well, I forgot what was the frequency, but there was some oscillations detected in the infrared, and then it turned out that this object also has optical oscillations at the same frequency, which kind of suggested that it's optical pulsations of the white dwarf, which are being intercepted by surrounding material and reprocessed, which kind of very strongly confirmed this interpretation that this is a circumstellar material which absorbs and re-emits this white dwarf emission. Now we have, thanks to Spitzer, we have a much better view of these objects. First of all, now we know more than 30 white dwarfs with near-infrared excesses. And this is a modern spectrum of the same object, G2938. You can see that it's quite well sampled thanks to Spitzer and some other instruments. There is an IRS spectrum over here showing this big bump. And you can see that now we have many more data points. This particular spectrum is fitted by assigning the white dwarf with a central temperature of about 11.5 thousand Kelvin, and then a single temperature black body to attempt to fit this near-infrared contribution. This is another example, also very well studied object GD362. Again, it has a nice Spitzer spectrum. It has this whooping bump at 10 microns. And anyone who has ever done or actually looked at the protostellar disk spectrum, like Juan, would probably immediately say that this is a spectrum of a protoplanetary disk. And that indeed looks like a spectrum of a protoplanetary disk. It shows the evidence of these micron-sized silicate particles giving rise to this feature. It extends far in the infrared, so it's very, very similar to what we are used to in the star formation and planet formation field. There are some key points that should be pointed out here. First of all, in many cases, single temperature black body, like here or in the previous plot, does not feed the spectrum very well. There are outlying points. That means that the material cannot be at a single distance from the white dwarf. It has to be spread out in distance so that it's heated to different temperatures and gives you an extended sort of multicolor black body. Second thing is that usually you find the lack of emission at long wavelengths. Protoplanetary disks usually have emission extending out to hundreds of microns and so on. But these disks around this circumstellar material around white dwarfs clearly does not extend too far, because there is no cold emission here, emission coming from cold grains. Yes, James? I'm not sure. I'm not sure actually about this. Herschel is very oversubscribed and not a very long-lasting instrument, and I'm not sure if Sophia can do as well. So. Sorry? Yeah, it's UV absorption, high temperature. Yeah, and these are just spectral lines. Okay, so this lack of cold emission basically tells you that the dusty stuff that intercepts the emission of the white dwarf does not extend beyond the 1 solar radius. So there is an outer cutoff to this dust around the white dwarf, which is 1 solar radius. It's a tiny, tiny radius. And usually when we talk about, when you look at this and think that this is a spectrum of a protoplanetary disk, you're thinking about an object that extends out to 100 AU or so. But in this case, you're talking about the dust extending out to only about 1 solar radius. And the temperature of this dust is pretty hot. I mean, it's between 1500 to several hundred Kelvin. Now, when you try to actually, take a sample of this model and try to model your spectra, all these data points quite accurately, this is what Jose, for example, was doing for some time, you find that actually a very good model, and the best fit in many cases, is reached if you just assume an optically thick and geometrically thin disk. That is, like effectively a solid plate that extends from some inner radius out to outer radius. That's totally flat. So it has a temperature distribution which is T to the minus R to the minus 3/4. Okay, and with this temperature distribution, you actually get a very good fit. And then this plate has to be really optically thick. It cannot be just a sprinkle of particles. You really have to have very high optical depth in this case. So if you think about what can such an object remind you in terms of these properties and in terms of the scales, the best analog is actually this. The rings of Saturn. The rings of Saturn also have an extent which is close to 1 solar radius. They're also extremely geometrically thin. They have a thickness of about several meters. And they have high optical depth. They have optical depth of order unity. So that's very, very close to what we see around these white dwarfs. And this is a sort of this is a representation done by John Debus of this is sort of to scale images of these disks around many, many different white dwarfs. So you can see that the analogy is pretty good, except that instead of the body which is 10 times the radius of the white dwarf and much smaller mass, you actually have a white dwarf with a solar mass sitting in a center with a size of about 1 Earth radius. Yes? Of the inner radius. Yes, you have a good estimate of the inner radius because when you have a spectrum, how high can the inner temperature be. If you would make the temperature even higher, you would actually get this part of the spectrum filled. And this part of the spectrum, near infrared, is very well sampled. So you actually have pretty good idea of the inner radius of the disk. Okay, so we have this interesting situation when we have these compact disks. Apparently, these disks cannot be primordial. I mean, they just could not have existed around this star when it was forming, when it was on a main sequence, because on a main sequence it must have had a much bigger size. So already at this point, you should be asking yourself a question of where did these guys come from? To add to this puzzle, in 2006, there was another interesting observational breakthrough. Boris Gansicki was using either KEC or VLT to try to better measure these absorption lines in the atmosphere of one particular white dwarf, SDSS 1228. And what he found, to his surprise, were not the absorption lines, but actually the emission lines. The emission lines of calcium, this is a calcium triplet, that looks very funny. The lines are split into this double-peaked structure. So when you see, and this is extremely strong signal because the error bars here are tiny. So you very well sample these lines. So when you see this double-peaked structure, it immediately tells you that what you see is a Keplerian disk, or at least a disk in a differential rotation around a particular object. Because then every spectral line gets split into two components. One is blue shifted, one is red shifted, and you get these two peaks. Then from the width of this, you immediately get the maximum speed that is reached by this emitting gas in this disk. And this velocity is about, in this case, it's about 600 kilometers per second. If translated to, if you know the mass of this white dwarf, if translated to the distance to this white dwarf, it would be about 20% of the solar radius, 20 or 30%. So again, numbers which are kind of roughly compatible with the solar radius, which is very, very, very interesting. Independently, no. I mean, well, yes and no. Let me show you the next. First, let me point out that very often you see that these lines are kind of asymmetric. And that may be interpreted in terms of the disk that's producing emission being, for example, eccentric. That's quite a natural explanation. Or that the emission pattern on the surface of axisymmetric disk is somehow non-axisymmetric. But I would prefer to not dwell on this, not speculate more on this issue. It's quite interesting.
Correlated with the infrared excess
So there are 7 disks now known that exhibit this gaseous emission with various levels of significance, but usually the significance is pretty high. And in all 7 cases, whenever you discover a gas disk around white dwarf, people would take Spitzer, look at this object, and they would invariably find these near-infrared excesses. So whenever you have a gas disk, you also have a dust disk. And then you can try to model gas disk and dust disk. And for the dust disk, you're getting the inclination. Because the inclination here is just the amount of flux that you're getting from this optically thick component. And again, Jose has spent a lot of time trying to break various degeneracies in this field. But you can actually determine the size of the gas disk from this width of the line, the size of the dust disk, the inner radii. The outer radii, of course, for the gas disk are not very well measured because you really need to be able to model the core of the line very, very well. So I would say that this lack of error bars is not very good here. For the outer edges of the dust disks, the situation is better. But what you find is that these radii are actually quite consistent with each other. So the dust and gas can actually be overlapping in radius. And then, well, it's not an independent evidence of the inclination, but it's probably hard to imagine that you have a gas disk that is not aligned with a dust disk. So they probably should be aligned. And then from the dust disk, from the inclination of the dust disk, you should know the inclination of the gas disk. Now, the opposite, of course, as I said, in all cases when we have a gas disk, we find the dust disk. The opposite is not true. We know about 33 or probably even more objects showing near-infrared emission, but only in 7 cases we see strong gas emission. And the gas emission is stronger around hotter white dwarfs, which is kind of reasonable because there is more excitation happening in these objects. And that probably might be explaining why we don't see the emission around gas emission around other objects. Okay, good. So this is all interesting observational phenomenology. So now let me move on to a little bit of theoretical interpretation and talk about the ideas that has been proposed for the origin of this refractory circumstellar material around the white dwarf and actually in its atmosphere. So when you have all this evidence, it actually starts calling to you for an alternative scenario of polluting these white dwarfs with metals, which is that these metals are coming not from the interstellar medium, but actually from the circumstellar medium, from some immediate vicinity of the white dwarf. And that's something that was first proposed by Charles Alcock in 1986 when he suggested that maybe it's the comets that are falling onto the surfaces of white dwarf, like the comets from the Oort cloud, that might be polluting them with metals. But at the time, these debris disks were not known yet, and kind of observation, this idea was too bold at the time. And it took some almost 20 years before Mike Ure in 2003 actually put this idea on a firmer basis. And the idea that Mike Ure explored is, was exploiting the fact that the outer radii of these disks around white dwarfs were about 1 solar radius. He noted that the Roche radius, that is the radius down to which a particular object can be approaching central mass without being tidally destroyed, in the case of white dwarf is about 1 solar radius. So if you take an asteroid or comet with a density of about 1 gram per cc and throw it towards a white dwarf, this object will be destroyed at a density, at a radius which is about mass of the white dwarf divided by the density of your object to the power of 1/3. And you plug in the numbers and you find that this is a radius of the sun. That's kind of an interesting fact based on the fact that this bulk density of the sun is 1 gram per cc, roughly, close to the bulk density of any other object in the solar system. So what happens then is if you somehow can take an asteroid or something, throw it towards a white dwarf, as it approaches 1 solar radius, it will be tidally shredded into pieces. And then the process should look something like the tidal destruction of a star passing near a supermassive black hole. And again, you would have initially the debris thrown out to very highly, almost parabolic orbit on a very eccentric orbit, coming back, colliding, producing gas, circularizing, and so on and so forth. This is the details of this process we are now investigating with Nick Stone and Brian Metzger at Columbia. But then eventually, these mutual collisions, these dissipative collisions, would lead to not only grinding down the big object into small pieces, but also to damping of any relative velocities and settling of all this mass into a configuration which is typical for Saturn rings, which is effectively, zero geometric thickness, very high optical depth disk. So that's the scenario that Mike Ure has advocated in 2003. Even before that, people have explored dynamically how that can actually happen. Debus and Sigurdsson in 2002, and then followed by some other publications, have looked at what would happen if you take a generally stable planetary system around the main sequence star, and then let this star lose mass and turn into the white dwarf. So if you had a system that was stable on sort of a gigayear timescale, this system can actually get unstable as the central star loses mass. In rough terms, the stability of a planetary system, if you have two planets with masses M1 and M2 separated by that same major axis of A1 and A2, then a stability can be evaluated by relating the Roche radius of the two planets. This quantity to the distance between them in terms of the same major axis. Now, when the white dwarf, when the star starts losing mass, the semi major axis of all the objects around it, be it a planet or a small asteroid, start expanding in inverse proportion to the mass of the central star. As a result of this, this ratio of semi-major axes does not change. I mean, they all change in the same way. But this ratio does because the mass of the central star is changing. So that then at some point in time, you can relate this ratio to its initial value. And the initial value, if it's very small, then a system would be very stable. And then this initial value would be multiplied by this additional factor, where the initial mass is much higher than is, well, generally higher by a factor of at least several than the final mass. So this ratio of the Hill radius to the separation in semi-major axis gets boosted up by a factor of several. And given the extreme sensitivity of the stability of the system to the value of this ratio, you can actually quite significantly destabilize the system and drive chaotic dynamics in it. And if in addition to the planets, you also have asteroid belts in the systems, then you will start kicking asteroids in all different directions. Some asteroids will presumably leave the system. They will be scattered out. But some of them will actually be launched on the low angular momentum orbits, which pass very close to the central star. And then if they enter the one solar radius away from the white dwarf, they will get tidally destroyed. And all this process, which I described on the previous slide, will be happening. So that's, in general terms, is a kind of dynamical motivation for this scenario, and this kind of explanation of why we see these characteristic sizes and of the white dwarfs. Now, there is some additional supporting evidence in favor of this scenario. First of all, if you just try to measure, count what is the mass of different metals in the atmospheres of these metal-polluted white dwarfs, that's a typical number. This is the mass of calcium in grams. The dependence on the effective temperature is not very important. And different, the open points are the white dwarfs without debris disks. The filled ones are the ones with the debris disks around them. What's important to take away is that this mass typically corresponds to the mass of a quite appreciable asteroid of the solar system, such as Minerva, Vesta, Ceres, and so on. And remember, this is a mass that's sitting in this outer convective zone right now. We don't know how much mass has already settled into the radiative zone of the white dwarf, and we don't know how much mass can be sitting outside in the possible disk around the white dwarf. Another interesting fact is coming from the relative abundances of different elements. So what's shown on this plot are the compositions of different elements for this white dwarf, which I showed before, GD362, which has very well-known compositions of many metals, compared to the compositions of the same metals, but taken in the Moon, Mars, and Earth. As you can see, there is a pretty good agreement between the different elements, between the abundances of elements in the inner solar system and the abundances of metals, relative abundances of metals in the atmosphere of this white dwarf. Sorry? Yes, they should be. Well, in the case of the Earth, I think it should be also. I mean, the iron at least should be boosted up by the content that's sitting in the core as well. So it should be sort of the full bulk composition. In particular, one notable point is that in all cases, in the case of the inner solar system and in this white dwarfs, we see very low carbon abundance, which is kind of natural if you think about the formation process of the inner solar system. But this point, this ability of measuring different elements, brings me to a very important point about that can sort of give additional points significance to these systems. These metal-rich white dwarfs are actually our only chance to ever be able to probe the bulk compositions of extrasolar minor bodies. Just think about it. How do we usually probe the compositions of any object outside of the Earth? This usually happens in a way that we either have to send a probe to it, like Rosetta, for example, or that we take some meteorite fall, break it with a hammer, take it in a lab, and do and do basically elemental analysis on it. In this case, the nature does a job for you. It just takes the whole body, it throws it into white dwarf, it shreds it apart. So it well mixes all the elements. It throws it into the effective mass spectrometer, which is a photosphere of this white dwarf. And then you take your telescope and just measure these bulk abundances of different elements. This is amazing. I mean, and you will never, ever be able to do this, for example, with transmission spectroscopy, with surface emission of directly imaged planets, and so on. Because this emission is probing only the outermost layers of the planets, which contain effectively zero amount of matter compared to the total mass. Yes? No. These are the asteroids which are continuously being scattered right now. Yes. The lifetimes of these disks are not very long, I have to say. There is observational evidence that suggests that they live between 10 to the 5 to 10 to the 7 years. Given well, but when you get the object tidally shredded apart, presumably everything mixes together. And then when it ends up on a surface, that should be pretty well mixed representation of the bulk composition of the whole object. People try to see variations of the absorption lines in the photospheres, but they don't see them so far. They haven't seen them. Why? Well, yes, but presumably you have a continuous accretion coming from the outside. So you're continuously feeding this process. So you should actually, I mean, as I said, the ages of these white dwarfs are comparable to a billion years. So you should think about possible multiple scattering events that would produce this disk that would live for, let's say, 1,000,000 years. Then it would go away. Then 10 million years after, another big body would come and will give you this disk. In the meantime, you might have smaller objects approaching, being shredded apart, but producing small disks, wimpy disks, which do not have a lot of near-infrared emission, but would still be polluting the surface of the white dwarf at some rate. So this is sort of the mental picture that you might have. But coming back to this point, I just wanted to show that indeed, in many cases, for many white dwarfs like this one, we have measurements of many different elements. You know, it's insane. I mean, 17 elements in some cases. So this they could be extremely good laboratories of the bulk compositions of the extrasolar objects. And to the point that you can actually start doing diagrams like this and making sort of geological inferences, like have a bulk composition of the Earth, plot different elements like iron, magnesium, silicon, calcium, oxygen, and say, well, usually you expect most of the oxygen to be locked up in olivines. So olivines are the compounds composed of magnesium, silicon, and iron. Then given my amount of magnesium, silicon, and iron, how much oxygen I will have left after all this oxygen was sequestered in the olivines. So usually you find that all of the oxygen is basically sitting in the olivines and there is nothing left. But in some particular cases like this object, GD61, you find that there is so much oxygen that it could not have been all sequestered in olivines. A lot of it was kind of free, and the most likely source for it was basically water. So about 1/3 of the mass of this object was in water. So it was a water-rich object eaten up by the white dwarf. I don't remember. I should check, actually. That's a good question. OK, so now let me talk about how actually, so I talked about the metal-rich white dwarfs. I talked about these presumed planets. Now, how do we actually get a pollution happening on the surface of the white dwarf? How does the matter gets transferred from this debris disk that surrounds the white dwarf onto its atmosphere? This is the current statistics of sort of just to remind you about how many objects are showing these properties. So about 50% of the white dwarfs are metal enriched. So if they do have these planetary systems, they have to be quite common. And then there is an interesting property that whenever you find a white dwarf that accretes at very high m dot, at very high rate, you actually find that it has about 50% chance of harboring near infrared excess, of harboring a debris disk around it. So you see that, yeah?
But you won't see the disk of its edge on.
Of course not.
The actual number must be a lot higher than
Yes, I would agree with that. Yeah. I mean, you would still, it's kind of not such a strong dependence that if it's inclined by 60 degrees that you won't see anything. But I totally agree that some of them could be hidden by just due to the geometric effects. And these are indeed just razor thin disks in this case. So here you can see that the dusty disks are these stars, and dust-free are without stars, and above approximately 3 times 10 to the 8, you have that about 50% of the sources actually harbor dust disks. That will be quite important for my the following story. So far, it's estimated that about 3 to 5% of just random white dwarfs, if you take a random white dwarf, it will have a 3 to 5% chance of having a near-infrared access and harboring a debris disk. And WISE actually has done a great job for us because it discovered a lot of these excesses, which are now being followed up slowly with the Spitzer. So the sample of this white dwarf has been steadily growing, the white dwarfs which show near-infrared access. And then another important point for the theoretical interpretation is that in all 7 cases when we have gas disks, we also see dusty disks. And also another important point is that whenever you see an near-infrared access, the central white dwarf is always metal polluted. So that's also inevitable. There are no metal-free white dwarfs that have debris disks around them. Sorry? No, I mean they are just presumably most of them are 0.5 solar masses. So okay. So now let me just describe some theoretical sort of mindset that at least I have for these objects. So here's a white dwarf in the center, and this solid part is it's kind of sliced in r theta plane. This is a disk of debris. I depicted it deliberately depicted it to be sort of razor thin. Then this disk is immersed in a gas, and the gas comes about because at some point there is a distance from the white dwarf at which the temperature of the solid particles becomes comparable to the sublimation temperature, which for silicon-rich objects should be about 1500 Kelvin or so. So basically, if you have a particle or if you have a disk that continuously moves towards the white dwarf, that continuously accretes, at this distance, particles will start evaporating, creating a gas of metals. Okay, and this disk should reflect the composition of the particles that it's composed of. So, for example, this gaseous disk should contain no hydrogen or helium, and that's precisely what we see because this gaseous emission that we see, we have only seen it so far. Coming from the calcium, magnesium, and iron. We have never seen hydrogen, we have never seen helium, although it would be quite easy to see. Then this disk extends only out to about 1 solar radius, and this sublimation radius is something on the order of 20% of the solar radius, because the radius of the white dwarf, this R star here, is about 1% of a solar radius. So roughly between 20% to 100% of the solar radius, you have this disk of dust. And then at the inner edge of this disk, you have a source of gas, this sublimation of particles, which produces gas. Now that gas should evolve. It should evolve because it presumably will have some viscosity due to MRI or some other process. And this viscous evolution will cause most of the mass to go towards the white dwarf. This is how you actually can get mass from the disk and transfer it onto the white dwarf, just the usual viscous accretion in this disk. But then to preserve angular momentum, as always in accretion disk physics, you have to have some gas going out just to preserve angular momentum. Not too much, but it has to be happening. And in this way, you're getting the gaseous disk, which is overlapping in its sort of radial extent with the disk of particles. This viscous evolution timescale in this metal gaseous disk is quite short. It's about several hundred to maybe 1,000 years at this sublimation radius. So whatever is governing the transfer of the rate of mass accretion onto the white dwarf should be not this viscous evolution timescale, but actually the timescale on which mass is transferred in the disk of solids, because that presumably is a much longer time scale. However, if you think about the processes that can cause the mass to go through the disk of solids, it's not very easy to come up with a process that will give you high enough m dot. We typically observe mass accretion rates of order 10 to the 8, 10 to the 11 grams per second. But if you, for example, try to use your knowledge or understanding of the properties of the Saturn rings and take the so-called collisional viscosity that happens just because of the physical collisions of particles in Saturn rings, propagate it to these disks and see what kind of m dot mass accretion rates you would get, they would be like 10 orders of magnitude below this measured mass accretion rates. So apparently collisional viscosity doesn't work. And at least for 5 to maybe 10 years, people were struggling to understand what could be causing this mass transfer from the disk of solids onto the star. Several years ago, I came up with the idea that this can actually be happening because of the radiative effects. Radiative effects around white dwarfs, I mean, initially you might be suspicious about the idea because white dwarfs are very faint. I mean, the luminosities of these white dwarfs are typically on the order of 10 to the minus 3 of the solar. But on the other hand, the matter is sitting very, very close, within 1 solar radius of the white dwarf. So what happens then is you have this flat disk of solids, and it's being illuminated by the white dwarf. And you can imagine that the white dwarf, for simplicity, it's like a spherical cow in a vacuum, right? You take a white dwarf, you slash it in halves, 2 halves, and you put one source of luminosity here on a lamppost, another one source of light is underneath. And then you are kind of illuminating the surface of the white dwarf at a slant incidence angle, which is about the radius of the white dwarf divided by the radial distance. So this is like a mental picture that I had in mind when I started thinking about this. Another important fact is that, as I said, the optical depth of this disk is high, even in the perpendicular direction. We know this from the spectrum. That means that if you're illuminating it at a grazing incidence angle, it should be even more optically thick to this incoming radiation. So effectively, all the radiation that's coming from the white dwarf gets effectively intercepted by the surface of this white dwarf. And then the relevant process that might cause the evolution of the white dwarf is the Poynting-Robertson drag. Poynting-Robertson drag, I'm sure, is known to all of you, but let me just remind you that this is effectively a especially relativistic effect that's related to the aberration of light, that a moving source see light aberrated by this angle, by this small angle, which is v over c. Then if you're sitting in a frame of a particle which is orbiting a source of light, let's say the sun, which in principle has radiation propagating only radially, and a particle is moving on a circular orbit, so radiation should be arriving perpendicularly, the particle actually in its own frame sees the radiation arriving at a small angle delta, this aberration angle. As it absorbs energy, it also absorbs momentum. And there is a component of momentum because of this aberration that will be acting in the azimuthal direction, producing azimuthal force, always acting in a direction backwards. It's like a wind blowing you in the face. And as a result of this, you have a torque that changes angular momentum of the particle and causes it to slowly spiral in towards the central star. And a typical time scale for a micron-sized particle around a solar type star at 1 AU is about several thousand years. In the outer solar system, it would be something like 1 million years, and you think that this process is responsible for emptying out the dust reservoirs around young stars, which are known to us as debris disks on a much bigger scale, around stars with ages of 10 to 100 million years. So this effect is very well known in planetary sciences. But now it's known in the context of just having particles with some particular sizes. How should I apply it to this case when I have a lot of particles with different sizes colliding with each other, interacting, and so on? So here how the calculation goes. I mean, you just take 1 square centimeter of the disk, and you consider the amount of radiation it receives. It's L star over 4 pi r squared times this geometric grazing incidence angle. You divide it by c because you're interested in the amount of momentum absorbed by this surface element, and then you multiply it by the aberration angle. This gives you the azimuthal force acting on a 1 square centimeter of the disk due to the Poynting-Robertson drag. And then just simply from the conservation of angular momentum, assuming some surface density of the disk, you get the radial velocity of this material. And then you very naturally compose this thing, which is mass accretion rate due to the Poynting Robertson drag, for which you actually end up with an amazingly simple formula. So you get that the mass accretion rate due to the Poynting Robertson is just the L star, the luminosity of the white dwarf, divided by c squared, and multiplied by this geometric factor, which is effectively r star over the distance. It's quite amazing, right? I mean, because this formula is completely independent of the density, of the surface density of the disk, of the properties of the particles, like their density and so on. It's independent of the sizes of particles. As long as the disk is absorbing all the incoming radiation, this is what you get, okay? And then you can just do a simple comparison with the reality. Instead of this r star, instead of this small r, let me plug in the expression for the inner radius of the dusty disk, this sublimation radius. If I do that, I get the following simple prediction, that the mass accretion rate due to the Poynting Robertson should be something like 10 to the 8 grams per second, multiplied by this quadratic dependence on the radius of the white dwarf, temperature of the white dwarf, and the sublimation temperature. These two quantities usually don't change too much. I mean, radii of the white dwarf are usually about 1% of the solar radius, but there is some dependence on the temperature, on the effective temperature of the white dwarf, which I tried to plot in this diagram. So in this diagram, the red points are the white dwarfs with disks, and the black ones are the ones without disks. And my theoretical lines are basically these blue ones. Let's say, the solid one. What you see is that whenever a white dwarf has a disk, the red ones, they're always sitting above this theoretical prediction. And if you think about it, this is exactly what you expect. Because whenever you have a disk, the Poynting Robertson should give you at least the m dot due to this effect. So there isn't, it would be really, really strange to find an object with a disk sitting over here, because that would mean that the Poynting Robertson is basically not working. But it should be working, and that's why you're getting this, sort of lower envelope to this disk hosting systems. So I was very pleased to see this comparison, but at the same time, it's quite obvious that in many cases you see mass accretion rates which are much higher than this rate given just by the Poynting Robertson. That suggests that in these systems you see something else, not just the Poynting Robertson, but some other mechanism driving accretion, and it could be happening at a much higher rate. So in the remaining couple of minutes, let me just very quickly describe to you our most recent ideas about what could be going on in this case. Again, reminding you this mental picture, we have an overlapping disk of solids and a disk of gas, which is fed actually by the accretion of solids through the disk, through this debris disk. And then when you think about it, now this is a slice in z phi direction, sort of in azimuthal direction of the disk. You have this disk of particles, which is sandwiched between the two sort of bodies of gas. The disk of particles tries to move with a velocity which is the Keplerian velocity. But the gaseous disk actually spins at a smaller velocity because it has radial pressure support. There is a pressure gradient in a gaseous disk which causes additional force that causes its azimuthal velocity to be lower than a Keplerian velocity. And the difference in the case of the white dwarfs is given by this formula. It's about 1 meter per second. It's a kind of weak breeze that's blowing over the surface of this disk of solids. But it's blowing all the time. And if you have any coupling, just pure frictional coupling, it will always induce a force that acts in a direction opposite to the rotation of the disk of solids. As a result, this causes the loss of angular momentum in the disk of solids, and it's a radial evolution. You see inflow of the solids towards the central star. So if you have ever dealt with a planet formation, you know that there is this 1 meter problem that is usually described in a very similar terms. Now, when you have this process going, you have the solid evaporating at the sublimation radius. They feed the disk of gas, which viscously spreads out and adds more mass to the disk of gas. As you increase the gaseous mass, you increase the coupling between the two disks. You increase the friction force. Increasing friction force means even more accretion in a disk of solids. More accretion in a disk of solids means even stronger evaporation, and so on. Under some circumstances, so apparently there is a positive feedback in this system. And under certain circumstances, the system may just go completely unstable. That's something that we investigated with Brian Metzger, where we basically tried to build models of the evolution of the solid disk surface density coupled with the evolution of the gaseous disk surface density. Initially starting without any gas disk, but then seeing how the gas was appearing because of the sublimation, growing in intensity, in density, and finally getting rid of the whole disk of solids due to this feedback effect. Just to illustrate this in terms of the mass accretion rates, what's shown on this plot is the mass accretion rates in units of the Poynting-Robertson mass accretion rate. And the time is expressed in a function of the viscous times. For our calculation, it was kind of natural to adopt these units. And the viscous time, let me remind you, is about 100 years. So this scale is about 1 million years. In the absence of the gas drag, in the absence of this coupling between the disk of solids and the gaseous disk, you would normally have the mass accretion rate, which is close to the Poynting-Robertson mass accretion rate, lasting for several million years. But with this feedback effect and with this runaway happening, what you have is actually you have a build-up phase when the gas in a gaseous disk is slowly increasing, and then at some point it becomes the coupling becomes so strong that you just basically wipe out the disk of solids on a very short time scale, and then the lifetime of the disk shrinks appreciably, and you also get a very strong spike of the inner mass accretion rate onto the white dwarf. So at the present moment, this is our best available scenario for explaining these high mass accretion rates, which actually doesn't require anything special, no special circumstances, and it uses pretty much kind of known physics. It's Poynting-Robertson and gas drag. Yes. Well, that's not quite true, because what I showed here is the actual mass accretion time, mass accretion rate onto the white dwarf. Then you also will have a settling time, so you will suddenly pollute the atmosphere of the white dwarf. So the mass accretion is estimated from the photosphere. This is a mass accretion into the photosphere. But then so how do you estimate the mass accretion rate? From the observations, people just assume that it's a steady state. While in this case, it's clearly not a steady state. And another thing, it only seems that this is like such a sharp spike. I mean, in reality, this is log plot, so it's a little bit better. Okay, let me. This is my summary. I just wanted to kind of. The purpose of my talk was to make you familiar with this beautiful object with a metal-rich white dwarfs, which we now understand cannot be polluted from the ISM, and are actually showing the evidence for the presence of the planetary systems around them. We see both gaseous disks, we see both dusty disks in a very compact configurations around these white dwarfs, which could be very, very old. And these disks are continuously polluting white dwarfs, and about 50% of the white dwarfs are being polluted by this material. So the evolution of these disks is primarily driven by the Poynting-Robertson-Drag and some non-trivial coupling between the gaseous and the disk of solids. And such objects, it's important to understand that these objects are our only chance to probe the bulk composition of extrasolar minor bodies, and also that they are telling us a lot about the planet formation and properties of the planetary systems around stars more massive than the sun. Recently, there has been a lot of controversy in the literature about whether there are planets and what kind of planets we have around stars, retired A stars, stars more massive than the sun. And so this is a very very subtle issue. So these white dwarfs actually are presenting you another chance to kind of study the population statistics after the main sequence evolution of these stars. And so just to conclude, let me also remind you that this is the future of our solar system, because at some point the sun will become this. Thank you.